Welcome to lecture 37. In our previous lecture, we started our discussion on thermocouples. So, in this lecture, we will continue our discussion on thermocouples. So, we will continue our discussion on thermocouples, which is a thermoelectric sensors. So, now let us talk about thermocouple materials. As of now, we have seen what a thermocouple is, how to make thermocouple junctions, what are the different junctions, what is Seebeck effect, Peltier effect, Thomson effect, and what are the different thermocouple laws. We have seen all these things in our previous lecture. Now, let us talk about thermocouple materials and different types of thermocouples that are available for measurement of temperature in laboratory or in industries. Thermocouples are manufactured from various combinations of base metals copper and iron, the base metal alloys of alumel, chromel, constantan, nicrosyl and nicyl. These are all alloys. Alumel is alloy of nickel, manganese, aluminum and silicon. Chromel is alloy of nickel and chromium. Constantan is alloy of copper and nickel. Nicrosyl is alloy of nickel, chromium and silicon, and nicyl is alloy of nickel, silicon and manganese. The noble metals platinum and tungsten, and the noble metal alloys of platinum rhodium and tungsten rhenium. So, these are the different materials which are commonly used for manufacture of thermocouples. So, we use these metals in various combinations to make different types of thermocouples. Each standard combination is known by an internationally recognized type letter. For example, type K is chromel alumel thermocouple. So, in industry, the thermocouples are known as a letter, is represented by a letter like say type E, type K, type J, type N, so on and so forth. We will take a look at the list. Now, type K is chromel alumel thermocouple. So, instead of saying chromel alumel thermocouple, in industry we call it type K thermocouple, and this is internationally recognized. So, everywhere type K thermocouple indicates a thermocouple which is made of a combination of chromel and alumel. There is also another point in it, like it always takes two dissimilar metals to form a thermocouple. So, we call one positive, another negative. We always use first one to indicate the positive metal, and the next we indicate the negative metal. For example, when I say the type K thermocouple is basically a chromel alumel thermocouple, the chromel is the positive metal and alumel is the negative metal. This is also well accepted and internationally recognized. So, we have list of some of these different types of thermocouples. Approximate ranges in degree Celsius unit is also indicated. So, copper constant and thermocouple is known as type T thermocouple. We will always indicate the positive metal first. So, copper constant and thermocouple, we have copper as positive metal, constant as negative metal. Copper constant and thermocouple can be used in the range of minus 140 degree Celsius to 400 degree Celsius. Similarly, chromel constant and thermocouple, which is known as type E, can be used in the range of minus 180 to 1000 degree Celsius. Iron constant can be used for 30 to 900 degree Celsius, and this is represented by letter J. So, type J is iron constant thermocouple. It is one of the most commonly used thermocouple in chemical process industry. So, this is very common, most widely used, one of the most widely used thermocouple in the range of 30 to 900 degree Celsius is type J or iron constant thermocouple. Similarly, chromel alumel type K, nitrosyl nicyl type N, platinum rhodium platinum thermocouples can be used for measurement of high temperatures as high as 1500 degree Celsius to 1700 degree Celsius. So, platinum rhodium 10% is one metal, platinum is another metal. So, this combination can be used in the approximate range of 30 to 1700 degree Celsius. Similarly, platinum and rhodium 13% and platinum can be used in the same range of 30 to 1700 degree Celsius. So, what it basically means is that here the positive metal consists of 90% platinum and 10% rhodium, and the negative metal consists of 100% platinum. So, this is type S. The next is the positive metal consists of 87% platinum and 13% rhodium, and the negative metal consists of 100% platinum. So, this is type R. This is a schematic of how the EMF output in millivolt varies with temperatures for different types of thermocouples. You can see in the figure that most of them are approximately linear. Not all are linear, but they are approximately linear. So, this is a schematic representation of variation of EMF output in millivolt with respect to temperature expressed in degree Celsius for different types of thermocouples. Now, let us talk about certain points about the common thermocouples. Platinum rhodium thermocouples, one interesting feature about this thermocouple is they are chemically inert, and they are also stable at high temperatures in oxidizing atmosphere, and that is why it can be used in temperatures as high as 1500 degree Celsius or 1700 degree Celsius. Chromel alumel thermocouples, they are mainly used in reducing atmospheres. The temperature voltage characteristic is quite linear for this combination. Copper constant on thermocouples, the upper range, which is 350 degree Celsius to 400 degree Celsius, is limited because of the oxidation of copper above this range. So, oxidation of copper may take place beyond 400 degree Celsius, and this limits the upper range for copper constant on thermocouples. Iron constant on thermocouple, this is most widely utilized thermocouple for industrial applications in oxidizing atmospheres to about 750 degree Celsius and reducing atmospheres to 900 degree Celsius. This is another summary of different types of thermocouples and their range of applications. Thermocouples made up of base metals, they are generally used to measure temperatures up to 1000 degree Celsius. Examples are type J, type E, type T, type K. Thermocouples made up of noble metals, they can be used up to 2000 degree Celsius or 1700 degree Celsius. These are all indicative ranges. So, if you look at different references, there may be a difference of say 100 degree Celsius or something like that at the higher range. So, they are thermocouples made up of noble metals, type R, type S, type B. Thermocouples made up of refractory metals, they can be used for measurement of even higher temperature up to 2500 to 2600 degree Celsius, type C, type D, type G. In reducing atmospheres, the thermocouple metals are contaminated at high temperatures by absorbing small quantities of other metals from nearby objects such as protective tube. This causes loss of calibration and is common to most thermocouple materials above 1000 degree Celsius. Thermocouple voltage. Now, the thermocouple always produces voltage in the range of millivolts, and that millivolt corresponds to the temperature difference for a given thermocouple that exists between the hot junction and the cold junction. So, I have to know that if thermocouple produces a particular millivolt, what that millivolt corresponds to in terms of temperature. So, it corresponds to a temperature difference. So, now we have said that for making a thermocouple an useful temperature measuring instrument, one junction must be kept at constant temperature. So, there are comprehensive tables you will see in different books where the EMF produced for the EMF produced by given thermocouples will be indicated if the reference junction is kept at 0 degree Celsius and the measuring junction temperature is at any given temperature. So, this table is useful source of information so that we can calculate the temperature of the medium whose temperature I am measuring when I know the millivolt produced by the thermocouple. So, there are comprehensive EMF tables that give voltage versus temperature relationship for many types of thermocouples. These tables give the voltage that results for a particular type of thermocouple when the reference junction is at 0 degree Celsius and the measurement junction is at a given temperature. For example, chromel-alumel thermocouple produces 29.14 millivolt when the reference junction is at 0 degree Celsius and the measuring junction is at 700 degree Celsius. Thus, knowing the millivolt produced by the thermocouple, we can measure the unknown temperature of the medium. So, for an application with chromel-alumel thermocouple, if the thermocouple produces 29.14 millivolt and the cold junction is kept at 0 degree Celsius, then we know that the measuring junction is at 700 degree Celsius. But it may not always be possible to keep the reference junction or cold junction at 0 degree Celsius. So, correction will be required and we will talk about that. So, this is how this thermocouple EMF table looks like. This thermoelectric voltages are given in millivolts and only a portion has been indicated. So, these informations are available in standard references in many books for various types of thermocouples and at various temperatures. So, how you read it? 250 degree Celsius, you have this is the EMF if the measuring junction is at 250 degree Celsius and the reference junction is at 0 degree Celsius. So, this is the EMF produced when the measuring junction is 256 degree Celsius and the reference junction is 0 degree Celsius. So on and so forth. You can read the thermoelectric voltage from this table easily. Now, as you see here, the table gives you what will be the EMF produced if the measuring junction is kept at certain temperature and the reference junction is always kept at 0 degree Celsius. Now, during your actual application, the output of the thermocouple will be a millivolt and you need to know what is the temperature of the medium or what is the temperature at the measuring junction. So, you have to look at the voltage here and then the corresponding temperature you will be able to find out. Now, it may be the case, in fact often it will be the case that thermocouple will produce a voltage that may not fall exactly on the table value. In such cases, we must interpolate between the table values that bracket the desired value, and this formula can be used for interpolation. Suppose my thermocouple gives me an output which is Vm millivolt. Now, I see the table and find out that there is no such value listed, but that there is a value which is slightly higher than Vm, let me call that as Vh, and there is also a value which is slightly lower than Vm, let me call that Vl. So, Vm is bracketed between Vh and Vl. Corresponding to Vh, I find that Th is the temperature of the measuring junction from the table. Similarly, Vl corresponds to measuring junction temperature TL. Then I make use of this formula for interpolation. So, measuring junction temperature corresponding to output voltage Vm is TL plus TH minus TL by VH minus VL into VM minus VL. So, this is a simple interpolation formula. So, let us clarify it further by taking help of a simple example. A voltage of 6.22 millivolt is measured with a particular thermocouple J type at 0 degree Celsius reference. Find the temperature of the measurement junction. So, a voltage of 6.22 millivolt is measured with a particular thermocouple J type, reference junction is at 0 degree Celsius. Find the temperature of the measurement junction. From the thermocouple EMF table, we see that Vm equal to 6.22 millivolt lies between V1 equal to 6.08 millivolt and Vh equal to 6.38 millivolt. I do not find any temperature corresponding to Vm equal to 6.22. The 6.22 is not listed in the table, let us say, but I see that there is 6.08, there is 6.36 and I have a value in between. So, corresponding TH and TL are 120 and 115. So, once I know VH and the corresponding TH, I know VL and the corresponding TL, I can find out Tm corresponding to Vm using the interpolation formula, and I find that the TA or the measuring junction temperature is 117.5 degree Celsius. Note that this has to be in between TH and TL, and that is also the case. So, as we are talking about the reference junction is 0 degree Celsius for those thermocouple EMF tables. So, in the figure we have an iron constantan thermocouple. Measuring junction is indicated here and the cold junction or reference junction is here. See, this thermocouple, this schematic shows a thermocouple with no extension lead. So, maximum accuracy is obtained if the extension leads are of the same material as thermocouple materials. So, we just keep the junction at 0 degree Celsius using ice bath, the millivolt produced will be taken as a measure of the junction temperature. Here we have not used any extension lead, any extension lead made of metals other than constantan and iron. But this is not economic always. Suppose you are using platinum, rhodium, platinum thermocouple, and this voltmeter may be located at some distance from the point of measurement. So, it is not economical to use a very long wire made of the same metals as the thermocouple metals, because it will be unreasonably expensive and there is no need also. So, we basically will use extension leads made from different materials. Here the thermocouple is made of iron and constant ton, but I have used copper as extension leads. See, the two extension leads that are coming from the voltage measuring device is joined with constant ton and with iron. See, of course, maximum accuracy is possible when you will have constant ton iron everywhere. So, there is no extension lead made of copper. So, the constant ton goes straight to the voltage measuring device, iron goes straight to the voltage measuring devices, and there is a single junction here. But as we discussed, that will not be uneconomic, that will be uneconomic, will not be economic at all. So, we will make use of extension leads which are made of different metals. Ideally, we should use materials for making extension leads which has similar thermoelectric behavior as the thermocouple materials. Now, when you use say copper as extension leads for iron constant and thermocouple, so I create two new junctions. Now, these two new junctions are kept at the same reference temperature 0 degree Celsius as shown in the figure. So, this will give you a fairly accurate result for the temperature measurement. Now, keeping the junction temperature at 0 degree Celsius may not be always practical. So, keeping the reference junction temperature always at 0 degree Celsius may not be practical. So, a practical approach will be keep these two new junctions at some constant temperature and known temperature, and then make compensation or correction for the changes in the reference junction. So, that is a practical approach, that instead of keeping these two new junctions at 0 degree Celsius, I keep it at a temperature which I can measure accurately, but both the two junctions are kept at same temperature. And then if I can measure the temperature, then I can make a correction or compensation for the change in reference temperature. How? We will see that now. Thermocouple tables are applicable only when cold junction is at 0 degree Celsius. To be able to apply thermocouple tables for non-zero reference temperature, a correction must be added using the law of intermediate temperatures. So, what I want the EMF when the thermocouple is kept at temperature TH and temperature 0 degree Celsius. So, TH is the measuring junction temperature, TO or T0 is the 0 degree Celsius. Now, if you remember our discussion on laws of thermocouples, when we talked about law of intermediate temperature, that if I take a thermocouple which works between temperature T1 to T2 and one EMF produces say E1, and then I take the thermocouple and consider the temperatures T2 and T3, and then in that case the EMF produced is E2. Now, if I consider temperatures T1 and T3, then the EMF produced will be E1 plus E2. So, this is law of intermediate temperature. So, the same law of intermediate temperature can be applied to find out the correction factor when we do not keep the reference junction at 0 degree Celsius. So, if let us say Th is the junction temperature, T0 is the 0 degree Celsius and Tr is the non-zero reference temperature. So, Tr is the temperature of the reference junction which is not 0 and it is somewhere in between the measuring junction temperature and 0 degree Celsius. So, higher than the 0 degree Celsius, let us say if you are measuring positive temperatures. So, I want EMF to be between Th and T0. So, I have T thermocouple between Th and Tr and thermocouple EMF between Tr and T0. So, if I now want to know the EMF produced between Th and T0, I have to sum this E1 and this E2. So, that is what is being done. So, that is what is being done. So, when you use a thermocouple for practical application, you have a non-zero reference temperature Tr and let us say measuring junction temperature is Th. So, you have EMF E1. Now, the thermocouple EMF table will give you EMF for Th T0 which is 0 degree Celsius. So, you need to know what is the EMF between thermocouple junctions temperatures at Tr and T0. If this is E2, you see that this will be E1 plus E2 according to law of intermediate temperatures. So, let us take a small numerical example, so that this becomes further clarified. Suppose we are measuring temperature of a fluid using a Cromel constant thermocouple. The reference junction is maintained at a temperature of 80 degree Celsius and the hot junction is immersed in the fluid. The output EMF is measured at 40.102 millivolt. What is the temperature of the fluid? Basically, I am going to measure the temperature of a fluid using Cromel constant thermocouple and the reference junction is not at 0 degree Celsius, it is kept at 80 degree Celsius. The output EMF is 40.102 millivolt. So, what is the temperature of the fluid? All I need to do is I need to know what will be the correction factor. So, what will be the correction factor? What is given? Reference temperature is 80 degree Celsius and the EMF produced between the hot junction temperature and the 80 degree Celsius temperature is 40.102 millivolt, that is the output of the thermocouple's millivolt meter. Now, I now need to find out what will be the EMF produced if I put the thermocouple in between two temperatures which are this reference temperature 80 degree Celsius and the 0 degree Celsius. From the table I find out that is 4.983 millivolt. So, now I must add this millivolt to this to find out what will be the EMF if the thermocouple is kept between temperatures, measuring junction temperature, that is fluid temperature, and the 0 degree Celsius. So, that is going to be 45.085 millivolt if I add these two numbers. Now, again you look at the table and you see that 45.085 millivolt corresponds to a temperature which is 600 degree Celsius. If this does not directly fall on any value in the table, you have to do the interpolation as we have seen previously. So, the fluid's temperature is 600 degrees Celsius. So, how do I do the correction? All I do is, if the reference temperature is not at 0 degree Celsius, you find out the EMF that will be produced if the thermocouple is kept between temperatures, the reference temperature and the 0 degree Celsius. That EMF must be produced to the thermocouple's output, and then you can directly look at the table. So, whatever we said can also be automated using a microprocessor based device, or let us say using a computer. So, the compensation circuit is very simple. All it has to do the calculation to find out what is the EMF produced when the two junctions are reference temperature and the 0 degree Celsius. So, what we do is, the new junctions that was produced by joining these extension leads are kept at same temperature using an isothermal block, and then I find the temperature of this isothermal block using an independent temperature measuring device. Usually a resistance temperature detector or resistance temperature device, RTD, is used. Then all these informations now can be processed using a computer or a microprocessor based device to find out the correction factor, and that can be deducted or that can be added to the thermocouple's millivoltmeter, so that I get the I can compensate for the reference junction. So, the compensation circuit develops a voltage which is combined with that from the measuring junction, such that the net voltage measured by the voltmeter is due to measuring junction temperature only. Finally, you can have various thermocouples in series. This combination, this is known as thermopiles. So, this is done to increase the output from the thermocouple. So, millivolt, the voltage that is produced by single thermocouple may be small. So, now if I connect several thermocouples and then we call it a thermopile. So, each thermocouple will be produced the same millivolt, and all these millivolts will be added together. So, the overall output from the thermopile will be much more. So, that will increase the sensitivity of the thermocouple, and it will be easy for the purpose of the measurement. So, this is an example of thermopile where we have connected various thermocouples, and note that all these junctions are kept at the temperatures T1 and T2. So, we will stop our discussion on thermocouples.